Hi everyone, thank you for joining us today for our webinar on compounding pharmacies. My name is Rachel Cox and I will be moderating today's event. This webinar is being brought to you by Antec Controls by Price and is accredited for 1 professional development hour. Before we begin, I would like to go over some administrative items. Audio is being broadcasted through the internet. However, if you experience any audio problems, please call in using a phone line and the phone number provided for you on your toolbar. Questions can be submitted anytime during today's presentation using the chat or the question function on your toolbar as well. We will try to answer all of your questions during the Q&A session at the conclusion of the presentation. After the event, all of those who have signed in will receive an email with a link to request your PDH credit for attending the webinar. Please give us 2 weeks to enter the PDH request and send you the certificate. And now to introduce the presenter and host for today's webinar. Our presenter for today's webinar is David N. David is in the Sales and Business Development for Antec Controls, has a Bachelor of Science in Mechanical Engineering, and has been with Price Industries for over 6 years. I will now pass the presentation over to David.
Thanks, Rachel. Good morning, everybody. Today, what we'd like to talk about is kind of an introduction to compounding pharmacies. And really what we'd like to cover today are standards USP 797 and USP 800. And really what updates have been made to USP 800 specifically, and how we can incorporate them into new or retrofitted design for compounding pharmacies. So the goal for today is number 1, to identify the engineering requirements for primary engineering controls, as well as secondary engineering controls, essentially meaning the equipment in the space and the space itself. We also need to be able to distinguish between hazardous and non-hazardous mixing spaces, and we need to be able to correctly select and lay out room pressure controls for a compounding pharmacy. That is kind of the end goal. And then lastly, we need to be able to show an understanding of the difference in airflow control types and their application in compounding pharmacies. So we'll start with a little bit of background today on the USP standards and the USP group in general, just to know where we're coming from. Then we're going to talk a bit about the applications, kind of the room itself and how it needs to work. We're going to move briefly into pressure monitoring and then into airflow control valves. And we're going to make some recommendations on those valves. And lastly, make a recommendation on room pressure controls and really what strategies to employ and what can work best in these spaces. Again, if you have questions along the way, please refer to Rachel's instructions. We can get those right at the end. So let's start with some background and standards. So USP is the United States Pharmacopoeia Organization. So it's quite an old organization. It was founded in 1820. And essentially, USP is a not-for-profit, science-driven organization that has an established process for convening independent experts for the development and maintenance of healthcare quality standards. So this group, for our intents and purposes, sets the standards for identifying identity, strength, quality, and purity of medicines. They've also made recommendations in these standards for how to build spaces around the compounding of those medicines. So the USP organization is not an enforcement agency. These USP standards are going to be enforced by the FDA in the United States. So now let's talk about these 2 standards, USP 797 and USP 800. USP 797 is the general protection of sterile compounds and spaces from contamination. So this was first released in 2004. It will be rectified with USP 800 later this year. The date for now is December 1st, 2019. So that's for sterile compounding. USP 800 is for the handling of hazardous drugs. Basically, USP 800 came about after reports were issued detailing how these drugs can affect the personnel in the spaces that are actually mixing these drugs. So again, this will be rectified and harmonized with USP 797 later on this year because there is some small conflict between these 2 standards. So USP 800 is really what we want to talk about today and really talk about the changes that are made in USP 800 and what they mean to our pharmacies. So there are a few compliance recommendations made here. The first is that a piece of equipment, a containment primary engineering control, or a CPEC, must be located inside a room that will function as a secondary engineering control, so a CSEC. This room needs to have an ISO Class 7 rating. The next change is that these rooms need a minimum differential pressure of minus 0.01 to 0.03 inside the buffer rooms. This is a little bit different than USP 797. USP 797 gave us a minimum pressure of 0.01, but it did not put a, if you want to call it, upper end cap on that number. So USP 800 is really locked in on this pressure range, and those two numbers there, 0.01 to 0.03, will be the difficult part of the design and commissioning of these projects. USP 800 also details that we need positive 0.02 inches in the anti-spaces. We need to maintain at least 12 air changes per hour in these spaces, though that number is changeable. We're going to talk about why it might need to be 30 air changes. And all of this air must be directly vented outside. So the other thing USP 800 brought in is that these drugs, we need to maintain this air change rate and this ISO classification not only in the compounding space, but also in the space where the drugs are stored. And the drugs must be stored and prepared in separate areas at this point in time. There is a small exemption permitted in USP 797 that lets you mix small volumes of hazardous drugs to be in the same space as non-hazardous drugs. I will define in a few minutes here what a hazardous drug is, what a compound is, and really hone in on what we're talking about in these pharmacies. But for now, we're talking just generally about hazardous drugs. So as designers, as engineers, as people working with these pharmacies, there are some costs and some considerations to make in these spaces. The biggest, I would say, is new equipment. So we need to maintain an ISO Class 7 rating in these spaces. So we may need to upgrade or introduce fan filter units. We may need to upgrade air handling equipment. We might have actually large changes to the facility required to separate hazardous and non-hazardous drugs. So a one or a two-room pharmacy may need to take up a larger footprint to become a two or a three-room pharmacy at this point in time. This may need some outside assistance and consulting. There aren't experts in these types of spaces. Even though a compounding pharmacy is not a large project typically, again, it's just 3 rooms usually, they are fairly unique and they're extremely critical spaces in a hospital. As far as cost go, the next thing we need to consider is the time. So we'll have more frequent environmental sampling, more frequent personnel assessment, more documentation and record keeping. And one I'd like to add here that I don't have listed is a much longer commissioning process. Because we need to maintain such a high air change rate to such a tight degree of pressure control, commissioning is ultra important in these spaces. And we will talk about that a little bit later on when it comes down to actually selecting a pressure control strategy. So now let's talk about the application. And let's talk about this pharmacy right here, this 3-room pharmacy. Don't get too hung up on the details of the ins and outs. This is just a generic overview of a generic pharmacy. But what you see right here is typically the pharmacy. Personnel enter through an anti-space that is positively isolated. To their right is another positively isolated non-hazardous drugs mixing space. You see a piece of equipment in there. And to their left would be a hazardous drugs, negatively isolated space. And you see some equipment in there. Don't get too hung up on the general exhaust, the supply, and the equipment exhaust. We will talk about that in some examples later. But generally speaking, this is the pharmacy we need to design. Now, when I say generic pharmacy, I make it sound sometimes like all of these pharmacies are identical, that they're very easy to design because they're cookie cutter. And while the general shape and form of them is, each pharmacy is truly unique. And again, that high air change rate and that tight pressure control make these some of the most difficult spaces to actually work with. So let's start talking about things to consider. What are these spaces doing? What are they used for? So there's 2 types of spaces in a pharmacy. There are buffer rooms and there are anti-rooms. Buffer rooms are the actual spaces where compounds are actually mixed in. Anterooms are those spaces leading into other spaces. And then there are two types of compounding. So there's sterile and non-sterile compounding. Sterile and non-sterile essentially defines the drug and the equipment used to mix the drug. Basically, if we need sterile compounding, it's because the drug requires that we prevent the ingress of microorganisms. So this isn't dictated by the space or anything. This is the drug and the equipment that we need to consider. When we're doing sterile compounding, we need at least 30 air changes per hour in that space. This is typically the type of room we're seeing. So they can get a little bit confusing here because we have sterile and non-sterile, we have hazardous and non-hazardous. So there exists full crossover between those. You can have sterile drugs that are hazardous or non, and you can have non-sterile that are hazardous or non. We can do some crossover on what these spaces can do as far as sterile and non and hazardous and non, and we will talk about that a little further on here. But first we need to define a couple things. I have thrown two terms out there quite a bit here already, and that's sterile preparation or drug. And what I'm talking about is a compounding sterile preparation, or a CSP. CSPs are the reason compounding pharmacies exist. Basically, there are drugs we need in a hospital environment typically that are not available over the counter or off the shelf. Basically, this isn't Tylenol and Advil we're talking about. These are things that need to be mixed in certain concentrations for certain patients in that hospital. Some of these CSPs are known as hazardous or sometimes as harmful drugs, or HDs. Now, a hazardous drug is basically any drug that has been proven to have positive effects on a patient, but will also have harmful effects. So if you think of chemotherapy, chemotherapy absolutely has a use in treating certain things. Chemotherapy also has some seriously negative downsides, but for the patient that needs that drug, the pros outweigh the cons. But let's take a step back and think about the person mixing up these hazardous drugs. They don't have this disease, and they would not see any of the benefits of these drugs. This is why these are classified as hazardous drugs. That person would only see the ill effects of these drugs. And the ill effects are classified in 5 ways. So you can see them listed there. So carcinogenicity, genotoxicity, things like that. These are the 5 classifications that if they harm a human in this way, they would be a hazardous drug. The 6th way to classify a hazardous drug is basically to say any new drug that looks anything like any of these other hazardous drugs is also caught under this umbrella, just to ensure safety of all the people mixing these spaces. So these are the drugs we're talking about, is compounding sterile preps that are either hazardous or non-hazardous. These need to be mixed and stored in different spaces. This is why you can see that 3-room approach appear in these pharmacies. Now, whether a drug is sterile or non-sterile, hazardous or non-hazardous, they need to be mixed in a certain type of equipment. Typically a biological safety cabinet, a laminar airflow workstation or workbench, or a compounding aseptic containment isolator. These are all just different layouts of equipment with gloves or without gloves, with a sash or without a sash, and some recirculation and HEPA filtration. There's a good mix amongst all of these. What we're seeing most often in the market is right at the top there. It's the biological safety cabinet. So this is an exhaust device that can be split into 3 classes. I'm not going to dig into what those classes do today. Basically, class 1 would be your lowest containment, if you'd like to call it that. Class 3 would be your highest type of containment. Again, we won't dig into that today. Most commonly, what we're seeing isn't just a biological safety cabinet. It's actually a class 2 biological safety cabinet. Now, amongst those 3 classes, we've picked class 2. Inside of class 2, there are 4 different distinctions of biological safety cabinet. Type A1, A2, B1, and B2. And again, I'm not going to dig in today what each of those means, but essentially it's a different amount of filtration and a different amount of recirculation and exhaust proportions amongst those devices. So this is the device that you see right here that we're most commonly dealing with. And the claim I'd like to make here is this equipment in your most critical space, which is your hazardous drugs mixing space, this piece of equipment essentially drives your design. And the reason I say this is the way the exhaust from this machine is handled is what drives our exhaust and supply system. This is what's going to dictate the operation of the controls. And the reason I say that, there are three distinct ways to operate these exhaust systems. By far, the most simple way to control one of these is to set constant volume. And we'll dig into airflow control technologies in a little bit, but this could be mechanically set constant volume. This could be a controlled constant volume. But the easiest way is to set it at, say, 500 CFM and never ever change it. The next way we might see this, and this is a fairly common approach, is to do a two-position type of exhaust. Basically operate at a constant volume until we need to fully shut this device off down to zero, whether for cleaning or decommissioning or repair. Now, as soon as we introduce that two-position control, we have introduced a variable volume into this compounding space. Now remember, this is high air change, not a very big space, controlled to a tight pressure. Any time in normal operation we're changing the airflow rate on the exhaust, including this two-position we're talking about, we're introducing some difficulty. So that brings me to my next point. The third way we can control this is full VAV. We could have different set points if the machine allows it for operating, decommissioning, shutdown mode, all of these types of things. But again, each layer, each different exhaust rate we introduce can introduce a layer of difficulty to these designs. So typically, and this is a very broad statement, it will not apply everywhere. Typically, we'd like to see these as a constant volume or a two-position type device. That is the most simple way to control this. Now I'm going to dig back into all those statements I just made when we talk about airflow control valves and technologies in a little bit here. I would like to touch on fume hoods here though, and basically make the statement that in compounding pharmacies, though we may call them sometimes flow hoods or fume hoods because it's a good generic catch-all term, in pharmacies we're not using typically your usual research fume hood. It's not a vertically moving sash or a horizontal or combination sash. These are not fume hoods. These are usually biological safety cabinets. Most manufacturers of controls will usually have a dedicated fume hood type control system. That's often not what we're employing here. I just wanted to make that kind of clear before we move on. So that's the type of equipment you're going to see. So you'll see that in some of the images coming up. There are a whole host of different pieces of equipment that will often help you to drive your designs forward. But there are a few types of spaces we can put them in. Again, to deal with different kinds of drugs we may need to compound. The first and most simple would be a non-sterile pharmacy. So you can see this would be like a class 1 bio cabinet. There's no anti-room, so this could not be done with hazardous drugs. This would be a non-hazardous, non-sterile pharmacy. This would be the simplest type of space we could design. Next up would be a sterile pharmacy. So this is where both the buffer and the anti-spaces need to have 30 air changes per hour. And because we have an anti-space here, we can mix hazardous drugs in this buffer space. We can also do sterile compounding of hazardous drugs because we picked the appropriate class 2 biological safety cabinet. You'll notice on both of these previous images, we have pressure monitors, and we're going to talk about those pressure monitors and where to put them a little later on here. But as I kind of started this presentation with, this is the pharmacy you're going to see requested most often. This is what we're seeing in the market. And it's your average 3-room hazardous and non-hazardous mixing space. So on the left is a negatively pressurized hazardous drugs mixing space. So we see ideally a constant volume bio cabinet or maybe two-position. On the right-hand side, we have some other containment device like a compounding aseptic isolator or a laminar airflow workbench in a positively isolated space. Splitting those two right down the middle is an anti-space. This is where we're going to enter these spaces. This is another positively isolated space. And you can see the pressure cascade that happens here. Essentially what you're seeing by those cascading arrows is air flows only into the hazardous drugs mixing space. It must at all times flow into that space. Meaning we need to maintain a pressure there of minus 0.01 in this space, minus 0.01 to minus 0.03. That is the difficult part about these designs. There is one other type of space you may see, In my experience, these are fairly rare. We don't see them very often, but it's a non-sterile and sterile combination pharmacy. So you can do both types of mixing in the space. You cannot mix between different types of equipment, and when you want to switch from sterile to non-sterile, you need to go through a cleaning procedure, essentially, in this space. These are, again, not very common. So now let's look at the room pressure monitoring. I mentioned there's a few different ways to do this, and there are a few different technologies to actually be employed in these spaces. So the first decision to make is where to place our pressure monitors and our pressure sensors. We need to make a distinction between those two. A pressure monitor is the display device. You can see one version here on the screen as well. That display device is typically located outside of the port of entry, outside of the door. So people walking into these spaces can clearly see green is good, I can enter my space. The pressure sensor that works with this monitor, however, you have two options of where to place it. So if you can see my mouse here, we can either place it between these two spaces here or between the corridor and that hazardous drugs mixing space. In a compounding pharmacy, what we're seeing most commonly is what you have on the screen here. But one thing to consider is when you're doing cascading pressures like this, any change to the airflow rates in your anti-space will affect the reading you get in your hazardous drugs and non-hazardous drugs mixing space. Meaning if the entire system is in stable and or constant volume, you will see pressure fluctuations in two spaces, even though you may only be seeing actual changes in one space. So this is a decision to make early on in the design before these are installed. Both are effective, both are perfectly fine. It's just a consideration to make about what you're actually going to see. So let's break this down. I mentioned we talk about monitors and sensors, and I want to talk about both of those individually here. So digital monitors are the way the world has gone with these. You can see one example up on the screen here. Typically, these provide a very clear visual display of what the pressure in the space is. And not even so much what the pressure is, but what the state of the room is. Typically, what you'll see from most of these is green is good. Green means I can go into a space. Red is bad. It means we're in alarm. You may want to see the pressure displayed all the time. You may not. Most monitors are capable of doing both. Typically, these will have alarms programmed in for high and low pressure and things like that. And you may even have caution pressures that don't audibly alarm, but only visually alarm. And again, most monitors are going to communicate with a building network. They'll typically talk over backend or some other network like this to communicate to the building how this pharmacy is operating. But that's just the monitor. I always want to make a distinction between the monitor and the sensor itself. They are two separate parts. A lot of monitors can work with a whole lot different sensors, and these sensors work in different ways. And basically what I want to dig into here is the maintenance cycle and the accuracy of these sensors. There's typically three types. The first, the most simple, and really you could call it the legacy technology, is a diaphragm sensor, sometimes called a differential pressure sensor. It's called that often. So these are very nice in that they don't actually transfer air between spaces. These are what we call dead-ended sensors. So there's no potential for lint or dust or dirt to actually contaminate this sensor because the sensing element doesn't allow airflow to pass through it. Now the downsides to this is they may drift over time. They may come with an auto zero function to help eliminate that. But over time, that diaphragm may stretch or change physically, and we need to recalibrate them. So this is where the maintenance cycle becomes associated with them. They are also typically not as accurate as other technologies we're going to talk about. As far as room pressure monitoring goes, they are typically accurate enough for these applications. The next technology you may be familiar with would be a hot wire anemometer. So hot wires are known to be more accurate than a diaphragm sensor. They also come at a slightly higher price point, typically. That's the trade-off you make for that accuracy. Now they are more accurate and they don't drift over time. There's nothing to stretch or change physically in this device. The one disadvantage you might see is air transfer actually passes over this device. So lint and dust and dirt may actually contaminate this device over time. So with these, you may actually have to have a cleaning cycle with them, not a recalibration cycle, but a cleaning cycle. The third technology we see out in the market is called a thermal MEMS sensor. Essentially, a thermal MEMS sensor is a hot wire anemometer almost, but it's shrunk down to a micro scale. And so what it does is it still measures the dissipation of heat. So what you will see in these devices is gas or an airflow essentially will flow into the device, and the temperature will be measured. A heater will heat it up with a known kind of set electrical input, and another temperature sensor will take that heat measurement again. And basically, the farther away this heat is seen to drift, the higher the airflow rate, meaning the higher the pressure. And those two values are correlated in these devices. Now, in your average thermal MEMS sensor, all of those sensing elements are pulled out into a silicon wafer. So they are pulled out of the airstream. So these are known to be very accurate like a thermal MEMS sensor, but they have extremely low potential for sensor contamination. And just like a hot wire anemometer, they do not drift over time. So when we talk about a maintenance cycle, this is another one of those added costs. We're trying to build a pharmacy here that's extremely tightly controlled and extremely well monitored. A drifting or a changing pressure sensor over time can really affect the maintenance and the operation of that space. So what we've seen here, and this is a test we did here, comparing a very, very high quality diaphragm sensor kind of as our experimental control. You can see that sensor in green. We compared that to a thermal MEMS sensor and a hot wire anemometer. So the thermal MEMS sensor is what you see in blue. Over time, this is almost 1 year of data with ash-ray dust basically passing through these devices. Ash-ray dust is this dark, carbon-filled, sooty substance designed to test HVAC systems. That's what's been passing through these sensors. So you see in blue that thermal MEMS sensor doesn't really drift over time, and it maintains that exact same measurement as the diaphragm sensor. And what you see is the hot wire anemometer starts off extremely accurate with those other two, but over time that slowly drifts down as that sensor can clog up. This is just something we like to note to say there is a maintenance cycle associated with some of these pressure monitors, especially in highly monitored and controlled spaces. But it may not just be the pressure that we want to monitor in pharmacies. We do also have requirements for air change rate, for humidity, as well as pressure, and even temperature eventually in the end we have to care about in these spaces. So you may want to display that in more places than just that pressure monitor on the wall. So a lot of manufacturers, us included, would also bring in a third larger display screen to display all of these network devices, typically just outside the anteroom and also sometimes right inside that anteroom for the pharmacy technicians to see as they're going about their day-to-day business. Now, I've talked about the pharmacy, I have talked about control a little bit and monitoring of the pharmacy, and really what we talked about most is the accurate control of a very tight pressure with a very large air change rate. So one of the most important decisions to make when designing these pharmacies centers around the actual airflow control valves that are used. Now, in this world, there are three types of technologies. All manufacturers will do this a little bit differently, but I'm going to lump these into three categories. Now, in these three categories, we have your typical VAV box seen at the top there. At the bottom, you'll see your Venturi valve, and in the middle would be what we call a high accuracy terminal. Now, each of these three devices performs, operates, works a little bit differently. And these are decisions we need to make early in the design process, and we need to rectify that with what the building current standard is, meaning what kind of pressure we actually have in these spaces to work with. So these are the three categories I lumped together here. So your average VAV box or a terminal unit, a high accuracy terminal unit, those are grouped together into mechanically pressure dependent devices, and then the mechanically pressure independent Venturi valve. So I'd like to describe a little bit how these each work. The legacy device in a lot of these spaces is your average VAV box. VAV boxes are extremely low pressure drop devices. They can work down to 0.01 inches of water column and still provide decent airflow control. They have a fairly modest turn-down ratio, and typically, as far as construction goes, they need 3 to sometimes 5 diameters of straight duct to get a decently accurate reading. Now, I say a decently accurate reading, meaning these are modestly accurate devices. These are not the most accurate airflow control technologies in the world. Some of the defining features of a VAV box are that they measure flow, and they measure that flow usually invasive in that airstream. So you can see we would have often a multi-point sensor in that airstream, capturing airflow, gathering an idea of what the velocity and total pressures are, and calculating an airflow from that. Now, with a sensor like that in the airstream, we do run the risk of contamination, whether it's from lint or dust or dirt, or even a Kleenex clogging one of these things up. Now, even with that nice, clean, straight duct upstream giving us the best reading we can get with a VAV box, like I said, VAV boxes are low pressure drop devices. Low numbers, like a low pressure, are very difficult to measure, meaning it's very difficult to control a VAV box to a very high accuracy and a very high precision point. No manufacturer will typically claim that the entire VAV box has been tested and can be controlled to plus or minus 5% accuracy. And that's the number I want to lean on here a little bit. Your sensor, your transducer, your controller, and your box, each individually might be good to plus or minus 5% accuracy. But when you build this whole device together, can it be controlled from minimum to maximum flow at plus or minus 5% of flow? And typically you can't do that with a VAV box. I'm going to come back in a little bit to why that 5% matters so much. But before that, I would like to talk about high accuracy damper control valves, or high accuracy terminals first. These devices, and again, this is where a lot of manufacturers do this differently. They create these boxes differently, but they do all lump together fairly well into the image you see here. These are blade dampers. They are nothing more than a blade damper. The blade damper portion, the mechanical way it functions, can be done differently. But in the end, this is a device that measures flow and moves some type of damper to correct that flow. This is just like a VAV box. This is a closed loop device. It measures flow and it moves a damper to correct for it. So some manufacturers will require up to 1 diameter of straight duct to give us a nice clean reading on that airflow sensor. Some of these are Venturi shaped, like the one you see up here, and those will compress flow through that Venturi section, basically eliminating the need for that straight duct. As we compress that flow, we create a nice clean airflow pattern, and what it does is it generates a pressure drop, and it generates or amplifies a pressure drop, making a number that's much easier to measure. These high accuracy terminals are often combined with a different type of sensing technology. We won't really dig into that today, but there are a few technologies to measure velocity or static pressures, to measure vortex shedding, and things like that, that can be used to control and measure the pressure drop across these devices. But typically, we're going to use a more accurate technology to measure these, meaning a better technology, meaning a slightly more expensive technology, to make this a device that can be controlled to plus or minus 5%. Most of these devices, most high accuracy terminals, can be controlled from minimum flow to maximum flow to plus or minus 5% accuracy. So these will be devices we more commonly look at in these compounding pharmacies. The next one, and I like to draw a line in the sand here between high accuracy terminals and standard VAV boxes. I like to draw a line in the sand between that and Venturi valves. Sometimes these devices look the same. I'm going to jump back one slide. Sometimes high accuracy terminals and Venturi valves look nearly identical. But these technologies are extremely different. They are not identical technologies. A Venturi valve is a mechanically pressure-independent device. A Venturi valve doesn't actually measure airflow. A Venturi valve measures the position of that internal spring and cone assembly you can see on the screen here. That position has been mapped out by the manufacturer, and based on the position, they know what the airflow rate is at any given position without actually measuring airflow. That's compounded with what's actually inside that cone. And what it is there's a highly engineered spring inside that cone. So what it will do, as the pressure drop changes in a system, this cone and spring assembly will shift forward and backwards. Basically, at higher pressure, it will compress farther into the valve. At lower pressures, it will expand out of the valve. And what it will do mechanically, without the use of a controller or a brain, is it will adjust the size of this orifice right here. You can see that circled right here. That orifice is then controlled at any given pressure between a certain set range. At any given pressure, it will provide the same known CFM flow rate. These are also controlled to plus or minus 5% of flow from minimum to maximum. The biggest difference here, as far as that goes, is typically a Venturi valve will have a larger available turn-down ratio as compared to a high-accuracy terminal. Typically about 16:1. You may even get up to 20:1 on a Venturi valve. Now, when it comes to picking a technology, I want to bring you back to that image of the biological safety cabinet. And we need to pick a technology to control that cabinet both accurately and effectively, but also cost-effectively. And I would recommend we use either a high-accuracy terminal or a Venturi valve to do that. I mentioned before there was 3 ways to do this. I mentioned you could do constant volume, you can do 2-position, or you could do full VAV. Now, I'm going to jump back 1 slide once more. Any high-accuracy terminal by any manufacturer, even any VAV box by any manufacturer, is a closed-loop device. It measures flow, and it moves a damper to correct for it. So whether we do this constant volume, 2-position, or full VAV, it's the exact same device. So on a biological safety cabinet, if we're going to use a high-accuracy terminal and hold it at a constant volume, that's the same equipment that's required to do full VAV control. And that's the same equipment required to do 2-position control. So this would not be the most cost-effective solution as far as first cost goes. However, high-accuracy terminals typically operate at lower pressure drops. Out of a high-accuracy terminal, you can get full flow at the wide-open damper position at about 0.15 up to about a 1/4 inch of pressure drop across these valves. A Venturi valve operates between 0.3 and 3 inches of pressure drop typically. So it starts out a little bit higher pressure drop already. But let's again think about that biological safety cabinet. We can do them constant volume, we can do them 2-position, or we can do them as full VAV. A Venturi valve, because it's a mechanically pressure-independent device, doesn't need a controller or actuator or any electronics to maintain a flow set point. That entire enclosure you see on top of the valve can be removed, and that linkage assembly right here can be mechanically locked into place. So for a biological safety cabinet, we could mechanically set this linkage in place to provide 500 CFM, independently of system pressure. This means we can provide the lowest cost option for that biological safety cabinet because there's no controls, there's no actuators, there's no networking required for this device. This is by far the most cost-effective way to control a biological safety cabinet. But it also provides you the least control over that cabinet. So what we are seeing most often on a bio cabinet is actually a 2-position Venturi valve. So inside that enclosure, we would just have a very simple relay system rather than a full controller, which means this valve can be open to some preset set point, let's say 500 CFM, or it can be closed down often to 0 CFM in the full shutoff position. Nothing exists in between there. So it's either operating or it's not operating. That would be the most cost-effective way to get the two set points you really truly need on a biological safety cabinet, and that two-position Venturi valve would be my #1 recommendation for these biological safety cabinets. We have rarely seen them as full VAV. When we see that, they are typically operating in some form of two-position as well. So now, we have talked about the requirements of these rooms, and it's very tight control of pressure, very high air change rate. We've talked about the equipment we might see in there. We've talked about how we would actually flow air through that equipment. But what we've been building to here slowly is how do we control room pressure in a compounding pharmacy? And this is a fairly hotly debated topic because there are two competing ideas of how to control pressure and how to maintain pressure. Unfortunately, both are often called pressure control, and both do create pressure, but there is a very key distinction between these two types of control. Both of them use an offset between supply and exhaust, and both of them rely on, we say a tightly sealed room, but I would like to just say they rely on a modestly well-sealed room. I'm going to come back to that comment. The first way to control these spaces, and by far the most common, even in laboratories and healthcare, would be airflow offset control. Basically, add up all of your supply and add up all of your exhaust and make sure there is a set CFM difference between them. This will create room pressure, but it operates completely independently of that room pressure, meaning as pressure slowly rises and falls due to natural phenomenon, the control system will not move to correct for it. This is as stable can be. This is the preferred solution typically. Often we're going to add a pressure monitor on top, and in a pharmacy that's actually a requirement to see that pressure, but those two will not have to talk to each other. The other control strategy is often just called pressure control. So again, it uses an offset between supply and exhaust, but it doesn't really care what offset it uses. It will just control directly to a room pressure. If it needs to slowly modulate its exhaust valve or supply valves, it will do that to achieve a set CFM target. Now, this is sometimes looked at as a better solution for a pharmacy. They need to be held to tight control. This looks like the easy answer to make sure that's maintained. But I made a statement earlier. I said we need a tightly sealed room. What can happen in these spaces is the rooms are too tightly sealed. They're too well built. Typically what we're going to use in these spaces is about a 10 to 15% offset. And when I say that, I mean in most critical applications. You'll have an offset of about 10 to 15% between your supply and exhaust. What we're seeing in compounding pharmacies is more so an offset of about 5%, sometimes even less than 5%. So when you have high air volumes due to your high air change rate, and you have an accuracy on your airflow control valves of plus or minus 5%, what we're getting is an offset that's too small even for the airflow control valves from all manufacturers. And so what pressure control can do inadvertently is fall into that accuracy range. Basically, the valve accuracy is affecting how well we can control the space. And what we can see from pressure control with really tight offsets, say of 100 or 130 or 150 CFM, is that even micro movements in your actuator can lead to a large change in airflow rate as a portion of your offset. 150 CFM offset quickly turns into a 200 CFM offset. That's a 33% change in offset in an instant. So pressure control looks like the solution. My claim here, and this is my opinion and my recommendation, is pressure control isn't the answer to these spaces. Stable volumetric offset is the answer to these spaces, just due to the tight control and accuracy available in these airflow control valves. There is another option available, and it is pull out all of the airflow control valves, just do a hard balance on these spaces. This still is preferred in some markets. We do see this being used. That being said, this may work on day one, but it doesn't allow for a very dynamic system on day two. We can't manage any changes in duct static pressure without bringing in somebody to fix that system or rebalance that system. So it's fairly uncommon in modern pharmacies. The last thing I want to do here before we make one final recommendation and then look at a couple quick examples is talk about actuator speed. A lot of times in this industry, in this market, we see high speed seen as a superior system. Speed of the actuator is sometimes correlated to quality of the system. And that's just not how a compounding pharmacy works. Compounding pharmacies are 99% of the time constant volume. Actuator speed shouldn't really be part of the conversation. The only reason we ever use a high-speed actuator in a pharmacy is sometimes on those biological safety cabinets to quickly drive from open to fully closed. In reality, in the grand scheme of things, that cabinet doesn't matter if it turns off in a few seconds or in a minute and a half. That cabinet's being turned off for several days or hours to be recommissioned or cleaned or worked on or something like that. So speed of the actuator really shouldn't be a conversation in these pharmacies. It's not a problem. Most manufacturers can provide high-speed solutions. My recommendation is to stay standard speed wherever possible. It's a much more stable, more cost-effective, and more simple system to employ. So, and we're getting here a little bit more to the summary of things, but what are our recommendations? Generally speaking, on your supply and general exhaust side, we would recommend a high accuracy terminal. It's lower pressure drop, it's a little bit quieter, and the first cost is a little bit lower. Because they have that low operating pressure, they can also often work with existing air handling systems. You may not have the pressure in this system to supply a Venturi valve with the pressure it needs. If you do, the Venturi valve is another very good option. On the biological safety cabinets, however, we would recommend a constant volume or two-position Venturi valve. That is the simplest and easiest way, as we already talked about, to achieve that simple operation and simple upfront first cost. So this is what that all ties together to look like. These are the types of pharmacies we're going to design. We'll typically have controls in each space. Supply and general exhaust will be basically constant volume and ideally high accuracy terminals. The biological safety cabinets will often be constant volume or two-position Venturi valves, and we'll have monitors at each entrance and sensors typically above each door to measure that pressure. And oftentimes we'll display all of that in a remote station, either for the pharmacy staff or maintenance staff in a remote location. So now we've got a few minutes left here before we get to questions. I'd like to quickly go through some examples. Now, this may seem fairly straightforward and simple, but it's going to bring up a few good points I'd like to talk about. We're going to design two rooms here quickly: a sterile hazardous drugs room and a non-sterile room. So a room at 30 air changes and a room at 12 air changes. So let's say our hazardous drugs room is 14 by 14 by 9 feet, giving us a volume of 1,764 cubic feet. To get the CFM, we take that air volume, or that volume of air, multiply the air change rate, and divide by 60 to get a required supply CFM of 882 CFM. In our non-sterile room with 12 air changes, maybe it's 10 feet by 10 feet by 9 feet, giving us a volume of 900 cubic feet. Our CFM required for this space, as you can see on the supply, would be 180 CFM. Now let's dig more into that sterile room. It has 30 air changes, and it's going to have a Class 2 biological safety cabinet, let's say, that is constantly exhausting 500 CFM. So we had 882 CFM of supply. We're exhausting 500 CFM. Currently, with no other equipment or exhaust devices in the space, we have 382 CFM extra of supply. But this sterile hazardous drugs room needs to be negatively pressurized. I made the statement we typically do 10 to 15% of offset. In this example, we'll do 10%. Meaning we need 882 times 1.1 for a total of 970 CFM of total exhaust in this space. Our biological safety cabinet is already exhausting 500, so some low-level exhaust, likely a high-accuracy terminal, will need to exhaust 470 CFM for this space. That number and the pressure created by those two relationships needs to be finely tuned and balanced on site. As design engineers, we like to say it must be 10%, it must be 82 CFM. That must have flexibility to be changed on site. It's up to the balancing and commissioning team to make that right. As engineers, we cannot hold too tightly to that number because we can't guarantee in the design phase what the construction of that space will be. Now let's look at the non-sterile space. Again, 12 air changes. It has a Class 2 CPEC exhausting 500 CFM as well. So we already have 180 CFM of supply and 500 CFM of exhaust. So we are short 320 CFM of supply already. Again, this is a negative space. We're assuming a 10% offset. So we need a supply air rate of 500 times 0.9, that's our 10%. We need a total supply of 450 CFM in this space. So in this space, instead of being driven by our air change rate, our supply and actually our true air change rate is dictated by the equipment. Now these are fairly simple examples, especially in the hazardous drug space. What we're seeing is typically not just one CPEC. We're seeing 1, 2, 3, even 4 of these devices in the space. So often we are driving much past the 30 air changes per hour that's required. We're seeing sometimes as high as 45 or even 60 air changes per hour in these spaces, making the accuracy of your airflow control valve, the accuracy of your control, the type of control strategy, making all of these different considerations compound themselves and become more and more important in these spaces. So kind of in summary here, just our last slide before we can get to questions. We talked about USP 797 and USP 800 in particular, and we really talked about the pressure and air change rates we need to maintain in the design of these newly renovated facilities. These are coming into effect to be enforceable by the FDA later this year, early December 2019. So we will see a lot of these projects on the go, hundreds and hundreds at a time. We talked about the airflow control valves. We talked about the pressure monitors and where to apply them and what types do exist. And we talked a little bit about room pressure control strategies. The last thing we did there was make a recommendation of typically using high accuracy terminals on supply and exhaust, and typically using Venturi valves, ideally constant volume or 2 position, on those different types of biological safety cabinets.